So I want to give a brief review of results we obtained in the last decade by now. And this is a list of collaborators that have been contributed to this program. And these are some faces in case you don't know them. These are my two students. And you also see non-Lattice people here because in this program we have to join forces with perturbative people doing perturbation theory, as you will see. So let me give you a brief motivation. We know from experiments, very different experiments, that the ratio between the baryon asymmetry and the photon density is of the order 10 to the minus 10. While we know that from the standard model, at least using electroweak biogenesis, we have a very, very different kind of order of magnitude. And we know since a long time that there are certain conditions that an interaction that has to generate this baryon asymmetry has to satisfy. And particularly the one we are going to focus is CP violation, because the interaction needs to violate CP. Now, a system which is very interesting to study discrete symmetry violations is the electric dipole moment of particles with spin. And the reason is very simple, is that the coupling between the electric field and the spin of the particle, which is the electric dipole moment, breaks time reversal. And if you believe CPT, this means it breaks CP. So you have been hearing lots of talk about this, and today now you listen about the electric dipole moment. So the electric dipole moment is able to actually probe very different scales from colliders. And the reason is that if you do an order of magnitude estimate of what the EDM would be of a fermion with flavor of a given flavor, you will see that if you assume maximal CP violation and a given order where this effect appears, then if you, for example, focus on the electron, you will see that the new scale physics corresponds to the order of 50 TeV or 2 TeV, depending on the loop that you are considering. So the discovery potential is that DDM is able to probe an uncharted territory in comparison with colliders. Now, if you don't insist that the new physics appears at the electroweak scale, then what you're probing with DDM is actually very small CP violating phases. So it still gives us an invaluable information for model building. Okay. So what's the status for the standard model? So there is no EDM at one loop, and there is also surprisingly no EDM at two loops. The quark EDM is generated at 3 loops, and the electron EDM, in fact, is generated at 4 loops. Now, of course, these are elementary particles, Feynman diagrams, so the electron EDM can be larger due to hadronic loops, and the electric dipole moment of non-elementary particles, like the neutron or proton, can be larger. And in fact, one can estimate, using effective field theories, the standard model, DDM stemming from the standard model, from the CKM matrix, and you will see this of the order of 10 to the minus 32 e centimeters. E is the charge of the proton. Now, experimentally, there's been a search of EDM as a long story, started in the 50s, and we still have no measurement of any EDM, any intrinsic EDM. But there's been an improvement of many order of magnitudes from the first experiment, and the latest experiment has a bound of 10 to the minus 26 e centimeters. And there are plans in the future, here I put a table with the biggest experiments, to reduce this by 1 and maybe even 2 order of magnitudes. In particular, the experiment of Oak Ridge, which is using a very different experimental technology, promises between, let's say, around 8 to 10 years, an improvement of almost 2 order of magnitude. So bringing this bound, hopefully, to 10 to the minus 28. Now, as I said, the standard model number is around here, 10 to the minus 32. This is just a cartoon of this plot here. And now here is where you want to hope to find a non-zero EDM, because in this region, there is no standard model contribution. It means that any measurement of a neutron EDM in this, between 10 to the minus 26 and 10 to the minus 32 is a direct sign of PSM physics. So the question is, can we actually disentangle? So once experiments are going to measure EDM, can we actually say what is the source of CP violation? What's the BSM theory? Now, at the hadronic scale, so what you do, you start from your high energy theory, you do the standard procedure, you integrate the heavy particles, and at the hadronic scale, you end up with a list of dimension 5 and 6 operators, which are known. And here I focus only on the operators that actually contribute to the, they're not all listed here, but the one I'm going to talk about a little. So one is the called quark chrome EDM, is a 2 quark, 1 gluon operator, which is CP odd. And then you have a 3 gluon operator, which is also CP odd, and some people call it Weinberg operator. And then there is also the coupling of the tensor charge to the photon. And there is also the theta term. So the theta term can also generate an EDM. And unfortunately, in Euclidean space, the theta term is imaginary, and the rest of the action is real. And so this action is complex, so it cannot be really simulated directly. So what people do usually is either insert a topological charge in your correlation function, so treat theta as a perturbation, which is a very safe approximation because, as you will see, theta should be of the order 10 to the minus 10 or smaller. Or some people rotate the theta to being imaginary, then do the simulation with the real action, and then rotate back to the real theta. I'm not following that route. Now, what is the role of lattice QCD in this type of calculations? The role is the following. So the EDM of a given nucleon receives several contributions. Receive a contribution from a theta term, and receives also a contribution from higher dimensional operators that you see here. And this, what I denote with M, are the hadronic matrix elements of the operator that are CP violating. So in this case would be the theta term, and in this case would be the hadronic matrix element of the CP odd operator. Now, in the US, there was a study report on fundamental symmetries and EDM, and this was the actual state of the art in 2022, where you see this in fact, is our lattice calculation, EDM lattice calculation, and then you see other contribution. This is the Los Alamos group calculation for the quark EDM. And these are, in fact, the quark chrome EDM, and these are estimated from some roots or for dimensional arguments because there are no lattice calculations for these quantities. And the same is true here. This is the contribution coming from the three-gluon operator. Now, these are some phenomenology plot that you can do. So here there is it's plotted the correlation of the proton EDM with the neutron EDM, and this gray band corresponds to the analysis based on, in fact, on our results of the theta term contribution. And it tells you that if you now use a different theory to generate an EDM, you won't be able to disentangle the two. Okay? So in order to disentangle the two sources of CP violation, you need to reduce the error on the theta term determination of the matrix element. So in particular, this band here is large because you see we have a very large error. This is not many sigma away from 0. And so the goal here is to try to reduce the uncertainty on the theta term determination. Now, there are other systems where one can try to find a non-zero EDM. In particular, there are certain heavy nuclei that are promising. But here the situation is complicated by the fact that in order to connect the proton and neutron EDM with the EDM of this heavy nucleus, you need some nuclear physics calculations, and these have a very large uncertainty. They essentially have 100% or 200% of uncertainties. And so this large band is, in fact, the combination of the fact that there are the uncertainties on the neutron and proton EDM is large because these are QCD sum rules, but on top of this, there is the uncertainty of these nuclear physics calculations. Now, for the theta term, the situation is also not great. And again, this band here is mainly due to the source of this band here is partially due to the uncertainty from the lattice determination, but there is also some uncertainty coming from the nuclear physics calculation. Bottom line is that if we will measure a neutron EDM in the near future, we won't be able to disentangle in this case if, for example, we measure also an EDM of the mercury. Now, very recently, a new system has been suggested to study this, to determine EDM, these are some molecules that have particular structures, and in particular, one can show that these molecules, once they are in an electric field, they respond in a way that they have a shift on this of their precession frequency, and as a matter of fact, from that measurement, you can infer what's the value of the neutron EDM, for example, and not only, also the electron EDM. And now you see here that this dashed line here is an old bound. In fact, the new bound is 10 to the minus 1. And very soon, they promise to go to 10 to the minus 2, meaning that very soon, this kind of system will have a similar sensitivity to the theta term as the neutron EDM. Okay? And this band here, in fact, is again, you see, this is actually 1 order of magnitude, this band. And the width of this band is actually, again, stemming from the uncertainty, partially stemming from the uncertainty of the lattice determination. So the bottom line is that in order to disentangle different CP violating sources, once we measure a non-zero EDM, or even if we don't measure a non-zero EDM, but we actually we have a better bound on the EDM, then we need to improve the the precision of the lattice determination in order to learn something about the CP violating sources. So, about the theta term. So to calculate the theta term contribution of the EDM, we have used the gradient flow to define the charge. This is by now standard. I just remind you that the charge, once you define it with the gradient flow, in fact, one can show that is independent of the flow time in the continuum. And at final lattice spacing, you would see that there are some, this is broken at short distance as expected. And this is a cartoon of what happens, but unfortunately, it doesn't work because of the, let's see this. Does that work? Yeah, but this doesn't work. Well, okay, what you should have seen is that this star goes around here and plateaus in the moment when all the ultraviolet fluctuations here are removed. So essentially, the flow is removing all the short distance fluctuations, and you remain with these structures, which give a non-zero value to the topological charge. To extract the form factor, to extract EDM, we need to determine the CP odd form factor. So you have to determine this matrix element here. You have to determine this matrix element, and then the corresponding CP odd form factor, which is called F3. And then the CP odd form factor at zero recoil is going to give you the EDM once it is normalized by the nuclear mass. So these are all the results. Here you see an extrapolation in Q squared of our form factors. There is a technical detail. We needed a variance reduction technique in order to improve in the signal to noise ratio. And the final result, you see it here in this blue band. And here you see the test of the independence on the flow time of the calculation of the CP odd form factor. These are three different flow times, and you see they're all consistent as they should. KPT is telling us that the dependence on Q square of the CP odd form factor is linear in Q squared, and in fact, that's what we see. It also tells us that there's actually isovector in a certain sense, both the EDM and the slope, which you might find in the literature is also called the shift moment. And in fact, this is what we observe for the EDM within our uncertainty. Now, this again is our whole calculation. This is the determination of the EDM. This is the EDM as a function of the pion mass. We had very old gauge configurations, very heavy, between 700 and 400 MeV pions. We had 3 lattice spacing, so we did the combined chiral continuum extrapolation. And what we observe is 2 things. The first is that we have a result that if you take the current experimental bound and you assume that the EDM comes only from the theta term, it gives a bound on theta, as I said, of order 10 to the minus 10. But most importantly, the log here has a coefficient which is G0, is the low energy constant. And this is our value extracted from the fit. And it is possible to actually use a completely independent determination coming from some axial, some chiral symmetry arguments combined with the determination of the neutron-proton mass splitting stemming only from QCD. And if you see, despite this is the most precise number, this is very well in agreement. This is, in fact, this is the number that is adopted in the phenomenological plot that you have seen earlier, okay, for G0. Now, to move forward, we have we decide to use new state-of-the-art gauge configurations, and so I need to talk a little bit about OpenLat and Open Science. This is OpenLat is an open science initiative. We generate gauges using exponential Clover and stabilized Wilson fermion setup, and this is the status of the runs, and these are the people which are involved in this effort, and the computer time for these kind of calculations have been provided by Prace and hopefully soon EuroHPC. So these are the first preliminary results on OpenLat gauges. So this is the isosymmetric point. So it's MPI 400 MeV. We have four lattice spacings from 0.065 to 0.12. And keep in mind that CV in this case is still missing. And this is the EDM continuum limit. On the left side here, you see the only difference between this plot and this plot is the separation between the source and sink. As Rajan was saying, and many people in this workshop have commented, there is the potential of excited states contamination. Now, if you see the scale on the y-axis here is very similar, and so if you try to compare point by point, I would say that within statistical errors are in pretty good agreement, but this is not so surprising because these are relatively large TSAP already. So this is around 1.2 Fermi, if I remember right, this is around 1.4. And also keep in mind that this is rather heavy pion, so the excited states contamination might be not so critical here. And, but what you notice also is that if you do the continuum limit, you get a rather good signal here, but if you do the continuum limit for larger t-sep, because of the larger statistical uncertainties, you find a number which is consistent with 0. So we need to do a better job both in decreasing the statistical errors here and also in trying to assess better the excited state contamination. Not saying anything about CV, by the way. This is the shift moment. So this is the slope in Q squared of the form factor. And you know, this contains relevant information because, for example, the leading order of the shift moment is proportional to that G0 low energy constant. And so if we are able to determine the two independently, it's going to give a very strong check of the calculation and independent determination of G0. And so if these are confirmed, as a matter of fact, despite the large error bars, if these are confirmed, this would be the first lattice determination of the shift moment. Okay, so this is a summary plot that was put in the white paper in this year, as a matter of fact. And these are the calculations which are available for the neutron EDM. There was an old calculation using KPT, but this calculation only estimates the chiral log. So the assumption here, the strong assumption is that the signal for DDM comes only from final loops. So the counter term essentially does not give any contribution. And this has been the common law in the community for 20 years. So then we calculated the DDM. This is the result I've shown you earlier. And then there were other calculations, in particular ETMC as a calculation at the physical point. So this is at the physical point at one lattice spacing. And then we have the Los Alamos, and don't be fooled by this band, is that here there are lots of systematics taken into account. They have lower pion masses than we have. And this is, I would say, very conservative estimate of the systematic for the excited states contamination and other systematics. But the message is that maybe the truth is not here and it's not here, but maybe it's in between. So we have to take care of assessing all the systematic uncertainties. There is a relatively new calculation that came out this year from K. Feiliu and collaborators, and so they claim this precision, and so if this is actually confirmed, this will be a great result. Okay, so the next thing I want to discuss is the quark-chrome EDM. So the quark-chrome EDM is a dimension 5 operators, which parameterize at hadronic scales to some BSM physics, and I write it here. And the problem, the reason why in the lattice community in the past there were essentially no lattice QCD calculation was that the renormalization of this operator is not easy. In particular, there is a power divergence. First of all, there is a power divergence. There is a quadratic power divergence because this operator mixes with absolute scalar density, and this mixing is not due to the fact that one uses Wilson fermions or break chiral symmetry. This mixing is there because they have the same chirality. So this mixing is going to be there even if you use domain wall fermions, for example. Additionally, if you use some Eremom type of scheme, depending on what lattice action, for example, if you use a chirally breaking action, then you will have also d = 4 operator, so you have another additional power divergence you have to subtract. And then you have some logarithmic divergence, so you have some d = 5 operators that contribute, and then there are also some other sorts of operators that you have to take care of because of the scheme that you're using. Additionally, I have to add that this coefficient should be subtracted non-perturbatively. And so this program is very complicated to follow through. So what we proposed was to use, in fact, the flow to define the quark-chrome EDM, but this time you have to flow the fermions. And additionally, this is not a situation like the topological charge where you know that there is no flow time dependence. So once you calculate your observable and non-physical and non-zero flow time in physical units, then you're done. Okay, essentially you have renormalized the charge. But in this case, the situation is different because these operators have a non-trivial running, and one of the things you have to take care in particular is the running of the float fermion field. So the float fermion field, even though at tree level shares the same property as for the gauge fields, so it gives you a smoothing of a range of around square root of AT, and also it provides you some Gaussian damping, a large momenta for the field. Nevertheless, the fermion field, the interaction needs to be renormalized. Okay, but the great advantage of this method is that any local bilinear or even 4 fermion operator, they all renormalize multiplicatively in the same way, and in particular, it renormalizes depending on the fermion content of the theory. So a classical example in lattice QCD where you observe power divergences is the chiral condensate. And now, if you calculate the chiral condensate at finite flow time, in fact, this renormalizes multiplicatively. So now the task is shifted to try to determine the float matrix element, which is relatively easy to renormalize, and then try to understand how this is connected with the physical one at zero flow time. So that's the task. Okay? So to do this, we use something called the short flow time expansion, and it works like this. You study your renormalized operator at non-zero flow time, and you expand it, and then you will have a contribution at t equals 0 with some coefficient which are logarithmically divergent if these operators have the same dimension, or are power divergent if the two operators have a different dimension, plus some higher order corrections in t. And now the strategy is the following. You calculate the lattice QCD matrix element on the left-hand side, then you calculate the perturbative matching coefficient, or if it's a power divergence, you have to calculate it non-perturbatively. And in this way, inverting this relation, you should be able to extract the renormalized quark chroma-DM at the physical one, okay? And this normalization is done either in the same scheme where you calculate the matching coefficient because the scheme dependence has to cancel out, or if you use everything in terms of RGI, Okay. So I go a little bit more in detail on the strategy because I think it needs some clarification. So, okay. I specify this is the quark chroma-DM, and I do a short flow time expansion. So I have a contribution from the pseudo-scalar density that goes like 1 over t with the coefficient here. Now this coefficient, in fact, runs, and it runs because both the pseudo-scalar density and the float quark chroma-DM run. Okay. And then you have some logarithmic corrections with a list of operators, okay, which you will see in a second. There are not many. And this matching coefficient here are calculable in perturbation theory. In fact, we have calculated those in perturbation theory. Okay. So to deal with the power divergence, what you can do, you can build a double ratio, two ratios. A first ratio is the quark chroma-DM at non-zero flow time divided by the pseudo-scalar density at zero flow time. Now, this ratio is finite. You see it here. These two objects renormalize in the same way. Okay, so I can do the continuum limit, and this is going to be just a function of the renormalized coupling. Now, the second term on the other side, because it contains the running of the pseudo-scalar density and the float fields, we'll have some non-trivial dependence on t, so we'll have some logarithmic dependence on t. Okay? But so this ratio, okay, because there is a t in front, this ratio, which is the matching coefficient here up toward the t, okay, you multiply by t on the left, and this becomes an order t. This matching coefficient is going to be the product of this object. They are both calculable in the continuum limit once this one is renormalized, plus some order t corrections. Okay. Now, of course, this order t correction will creep in and will contribute to the logs of the matrix element. So this is the matrix element. And so the power divergence can be subtracted non-perturbatively and in the continuum, calculating this finite piece plus the matching of the pseudo-scalar, times the matching of the pseudo-scalar density. So this is your matrix element. And you have a linear combination, which I didn't write for because it's a little long. You have a linear combination which depends on the matching coefficient, which are calculable in perturbation theory, and the two matrix elements. One that you can, again, in principle, calculate on the lattice, okay, because this object is easy to renormalize. You need just ZP. And as a matter of fact, it turns out that you don't even need ZP because in this particular linear combination, ZP cancels out. And the matrix element that you're interested in, which is here. Okay. So let me break this down. Okay. So on the left-hand side, you need to calculate this matrix element on the lattice. To calculate this matrix element on the lattice and do the continuum limit, the only thing you need to determine is Z chi. Okay. So the normalization of the float fields. This is we are working on that. Now, then, for the power divergence, you need the finite normalization between the quark chroma-DM and the pseudo-scalar density. This is done. It's finite. You can do the continuum limit and study the dependence on the coupling. Then there is the contribution coming from the pseudo-scalar density. Again, to calculate this ratio, you need Z chi. Okay? And as you see from here, it seems like you need also ZP, which won't be a problem because ZP nowadays is a standard calculation. But it turns out that when you put everything together, in fact, you don't even need ZP. You just need Z chi. Okay. Then these coefficients are calculable in perturbation theory, and we have done our homework. We have calculated this at one loop for all the operators you have seen, so for the quark chroma-DM and for the 3-gluon operator, and also there is a calculation for CP odd 4 fermion operator. And we are currently working on a 2-loop calculation. Then what one needs to calculate is the matrix element you're interested in. So in this case, it's the EDM. With the insertion of the pseudoscalar density. And as I said, here I put PR, but as a matter of fact, in this linear combination, ZP cancels out. And so in principle, one would just need the bare matrix element of the pseudoscalar density between two nucleon states, for example. And then the output of this analysis is going to be the matrix element of the quark chrome EDM at zero flow time. So step one, the power divergences. So we define a ratio. In order to calculate the power divergences non-perturbatively, we define a ratio between, we probe the quark chrome EDM and the pseudoscalar density with another pseudoscalar density. So this is gauge invariant. Okay, this is gauge invariant. You can build a ratio. Now this ratio is finite as a function of G bar squared. This is a normalized coupling. And you can do the exercise of doing the continuum limit. And this is analysis. And this green line is the one loop perturbative result. And that helps us in following the G bar square dependence of this finite normalization. Okay? So the next step after we have calculated this will be to calculate the matching of the pseudoscalar density. Okay? Okay. Now, for the higher dimensional operator, we can use perturbation theory, as I said. And this is the sketch of the perturbative calculation. We need to set up a matching condition, which you do in perturbation theory in this way. And in perturbation theory, you can calculate Zi, as you will see in a second, in a rather straightforward way. In order to do this, you define something called ring fields, which define the normalization using this. This is a normalization condition that fixes Zi in actually regularization invariant way. That's important because this procedure has to be used both on the lattice when we define Zi, but also in perturbation theory. Okay, so we did that. And there are results for this renormalization at one loop, but also at two loops. And then we have calculated a matching coefficient for the quark chrome EDM. This is a subset of the Feynman diagrams that we needed to calculate. This in particular is the matching of the quark chrome EDM into itself. The red box are the additional diagrams due to the flow. These ones are the standard diagrams at t equals 0. And despite it seems like an order of 2 or 3 more complicated, in fact, the machinery that experts have in this type of calculation doesn't make this calculation much more complicated than the case of t equals 0. But here you see the logs, okay, and you see the finite part. There is one technicality. You need to define gamma 5, and so we use two schemes to define gamma 5, Todd-Feldman, and also naive dimensionalization. And the difference is this delta HV, which is 1 in one case and 0 in the other case. Okay, I can skip this. So the status is that the normalization for the theta term and for the theta term, what we need to do is to improve the signal to noise and clean up our lattice calculation for having more source-sink separations. For the quark chrome EDM, the normalization program in perturbation theory one loop is finished, and we are extending this to 2 loops. For the non-perturbative power divergence matching, the finite normalization is done. Now what we need to do is the matching of the pseudoscalar density. So for the 3-gluon operator, we have calculated the matching in perturbation. This is a paper that we submitted last week, 2 weeks ago, I remember. This calculates the matching of the 3-gluon operator at one loop. And we also have some preliminary studies for the non-perturbative power divergences. And this is a summary table, which is useful to understand what's the status. Unfortunately, I have only 3 colors, and so there are some dots which are most likely in between. So, for example, this quark chrome green in normalization, I would say, is between yellow and green, maybe closer to yellow, but I want to be optimistic. And for example, let me see. Yeah, for the quark chrome EDM, we also have a first estimate coming from the Los Alamos group who uses leading order normalization. So, so in any case. So this tells you that somehow there is an EDM which is well under control, which is the quark EDM, but for the other EDM, there is still some work to do. But I think the method is pretty clear, and we're making good progress. And the hope is that for the theta term, so again, close here, the hope is for the theta term, we can reach an order of 10-20% precision in the next 2 to 3 years. Extension to loops is ongoing, and so now we have to put all the pieces together and extract the quark chrome EDM matrix element. There is one ingredient which is still missing, which I told you, which is the calculation of Zi. Thanks.